Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, we're going to start looking at some Cloudy output. Before we do that, let's get some of the jargon out of the way. This is the geometry we're going to compute. There's starlight coming from the left, creating an ionized layer on the surface of a molecular cloud. So the energy source for this ionized layer is the beam of starlight, which is a beam that comes in from a star cluster. We specified the beam of light as part of the input deck. Here's our geometry with a cartoon taken from Hazy, showing some of the jargon that comes with it. The radiation field from the star is referred to as the incident continuum or the incident SED. That means this is what is incident upon the surface of the molecular cloud. That beam of light then goes into the molecular cloud, striking the illuminated face. The illuminated face is this bright rim that we see as a surface atmosphere on the cloud. The beam of light causes the ionization and heating and is attenuated as it goes into the cloud itself. So that as the beam of light goes in, it's attenuated, and at any point you're looking at the transmitted continuum. That means the transmitted continuum is the incident radiation field into the cloud that's been attenuated by extinction due to the opacity sources. The geometry has two regions. The illuminated face is the bright layer we see. That's where the full force of the radiation field is striking the gas. So that will tend to be most ionized and hottest. It's also the brightest because the only source of power this emission has is the starlight from the star cluster. So the full incident radiation field strikes the illuminated face that's transmitted through. The shielded face is the far side of the cloud, which is basically in the shadow from the starlight, and will tend to be darker, colder, and more atomic. The diffuse radiation field is the radiation field nearly isotropic produced by atomic gases in the cloud. So this might be spectral line emission, Brem's emission, Thompson scattering really would be part of that. It tends to be isotropic and is part of the rate of transfer calculation. So this is the diffuse, this indicates the gas itself producing this diffuse emission. The reflected continuum, the reflected SED, is counted in this jargon as any light that comes back in the 2 pi steradian of the illuminated face of the cloud. So anything that comes back in this direction. So this would include part of the diffuse emission from the cloud. It could be part of the incident radiation field that backscatters off dust. So there are several sources of this. So out in the universe, when we look at this, what we see is the emission from the illuminated phase, this reflected continuum. Not much emission, half the light from this layer goes into the molecular cloud, but that is absorbed by dust inside the cloud. So that really does not get out into the universe. Some more words that come with it. This is on the left, our friend, and on the right, a very symmetric planetary nebula. There's two limiting cases for doing the rate of transfer. An open geometry is assumed by default, and we didn't specify that in the input deck. So the open geometry is one where the diffuse emission from the illuminated face is not going to go off and strike more clouds, so it doesn't need to be included in the rate of transfer work. In a closed geometry, like this beautiful 1D planetary nebula surrounding a central star, any radiation that escapes from the shell back towards the star, this reflected light, will go on and strike the far side of the cloud. So it's a symmetric case. This is assumed, it's called a closed geometry because it looks closed. And this is assumed if you use a sphere command. The issue region we're dealing with did not. Some other things for the geometry we're going to find when we talk about the save command is first the radius. We specified the radius as the distance from the illuminated face of the pillar to the star cluster. So it's about 2 parsecs. So that's just the radius in the cloudy input deck, but that's all. It could also be referred to as the inner radius. The outer radius would be the distance to the shielded face. So the illuminated face is the inner radius. The shielded face is the outer radius. We're going to be looking at a lot of save files in the next video, and it's going to tabulate quantities along the ray going through into the cloud, and it's going to tabulate them versus depth. So depth is the distance in the cloud from the illuminated face to the point in question. So these jargons out of the way, we're going to dive into the output from the save files and create some plots to see what we predicted.